So the utility in equilibrium expressions is they allow us to compute the concentrations of certain species like ions in water, especially in the presence of other stuff in water. And so you've done this in a Chem 108 course. You've learned how to make an ice table or an IE table, depending on where you learned it, to compute what the concentration of a particular species would be, especially an ionic solid that dissolves into ions. When it reaches equilibrium. And so we're going to start there, and we're going to do that with calcium sulfate as a solid, and just think about, remember very quickly how we do that, just thinking about calcium sulfate as the only equilibrium at play and the only species that's important. So calcium sulfate, one form of it is also known as gypsum, which I'm showing you here. So this has big implications on things like aqueous geochemistry. So if you're an aspiring geologist, this is a pretty important thing to consider. It's also really important, this same notion of computing solubility equilibria is really important in medicine, because you can imagine a lot of medicines are taken orally as a pill in a crystal form. And so you take that pill, it's going to dissolve to reach some equilibrium based on the solubility and the conditions inside the system, which again is going to be a function of what's already there, like the common ion effect. So I'm going to walk you through these three scenarios. One, calcium sulfate dissolving by itself, which is what you're familiar with. One, in the common ion effect. So if we just toss in some extra sulfate in the form of potassium sulfate, how does that impact that? And then we're not gonna do this one quite yet, but we're gonna do it in a future video. What happens if you have just salt in the solution where there are no common ions? So you've got potassium and nitrate, but those differ from calcium and sulfate. How does that impact the solubility? And I think that's going to be something that's new to you. You may have some intuition there. You may not. This may come as complete surprise. But in order to treat this one mathematically, we're going to have to introduce a new concept called activity, which we're going to do in Chapter 8. So we're going to start with just the solubility of calcium sulfate by itself. And so as we'd already discussed, anytime you're talking about solubility, the equilibrium constant for that, or specific to that type of reaction, is going to be KSP. In this case, that value is 2.4 times 10 to the minus 5. And we're always going to write this out in the dissolution direction, meaning we're going from solid to dissolved ions. So we'll write this out as calcium sulfate solid, double arrow to indicate the equilibrium in both directions, calcium 2 plus, which will be an aqueous ion, but I'm going to skip that, plus sulfate. And I'm giving lots of space here because, as you're probably anticipating, I'm going to craft an ice table. And so this is the directionality, right? Dissolution. Ice tables stand for initial, change, and equilibrium, and we're going to input concentration values here. Ice tables, you may love them, you may hate them. Really, you shouldn't be intimidated by them because they're simply just tables of accounting, just to see what we have and what we change so that we can do the algebra more simply. And you're going to do several of them. Your book skips the change part and just does IE tables. I guess that's the move from Gen Chem to an analytical chem course. It doesn't matter. You can use either. I'm going to do this one as an ice table just to get the ball rolling here. So when we're thinking about using an ice table to compute the solubility, what we're really asking is, well, how much of this original solid breaks apart and how much calcium ion and sulfate ion do we yield in the beaker, right? So we've got this beaker here. We're going to toss a chunk of that gypsum in here, and we want to know, because at the beginning our calcium and our sulfate ions are equal to 0, right? We don't have any of that stuff in there, but we know that based on this being a non-zero value, which it'll always be a non-zero value, that some finite amount of calcium 2 plus and sulfate ion will be present after some finite amount of our calcium sulfate solid actually dissolves into the beaker. So at the beginning, we don't have any calcium sulfate in the system, so we have 0. We don't have any calcium ion in solution, so we have 0, and we don't have any sulfate ion in solution, so we have 0. So that's an easy fill because nothing's happened. So initial means pre-equilibrium or pre-change even, before we've allowed the system to start to proceed towards equilibrium. In terms of change here, some amount of this original solid, regardless of how much we have, it could be 10 grams or 100 or a kilogram or whatever, some amount of it, some mass of it is actually going to dissolve. So that means some amount that we had is going to be lost as it dissociates into the ions. And so we can signify that as a loss of X. Some amount X of that stuff is going to break apart. In this case, for every 1X, based on the balancing coefficient here, for every one of those formula units of calcium sulfate that dissolves, we're going to get one ion. So 1X dissolves, 1X actually turns into the ion, and the same is true because of the simple 1 coefficients in front of calcium and sulfate. So we get a plus X plus X. And so our sort of equilibrium concentration here is going to be technically 0 minus X. This actually won't matter because calcium sulfate doesn't factor into the equilibrium because it's a pure solid, but it can be helpful if we do know how much of the mass we started with, how much will dissolve. So we'll have X at equilibrium, and we'll have X at equilibrium for sulfate as well. So we can punch this into the equilibrium expression, which we know to be KSP equal to the concentration of the products of the ions, being calcium concentration and sulfate concentration. So this whole thing is going to equal X times X equals X squared equals our KSP, which is 2.4 times 10 to the minus 5. So if I take the root of both sides, I'll say X is equal to the square root of 2.4 times 10 to the minus 5, which if you compute this value, this comes out to be 4.9 times 10 to the minus 3, and we're talking units of concentration because that is the expression we're using. Remember, that's the implicit assumption, is that we're using units of molarity, moles per unit, or moles per liter. So we end up with 4.9 times 10 to the minus 3 molar, or roughly 4.9 millimolar. So that would be the concentration of both sulfate and calcium, because both of those are X at equilibrium, right? This is X that we computed. So at equilibrium, that's the concentration we'd expect for both of those ions to be in solution. So at the same time, when we talk about this concept called molar solubility, sometimes I'll ask you that, or your book will talk about that, or somebody else may talk about molar solubility. What they're referring to is how many moles per liter of the original solid can dissolve. And so in this case, because we have a balanced coefficient of 1 here, and 1 here, and 1 here, this is really convenient because X is the amount in moles per liter of the calcium sulfate that is allowed to dissolve at equilibrium. And so the molar solubility here is also the same as X. So if we were to try to report, well, how soluble is calcium sulfate, in this case at 25 degrees C, we would say its molar solubility is 4.9 times 10 to the minus 3 molar. Coincidentally, that is also the equilibrium concentrations of both calcium ion and sulfate ion in this case. But it won't always be coincidence in that case if the coefficients aren't simply 1 to 1 to 1. Okay, so that's sort of the big picture for solubility for this step 1, right? Or this example 1, where we're considering just the solubility of a solid by itself. So let's move to the example 2, which is the solubility of this same thing, but let's compare it when we have a common ion. So I'm just going to put up here by itself, we got a value, molar solubility value of 4.9 times 10 to the minus 3 molar. And then we'll compare that after we do the common. Okay, so second scenario, we've got calcium sulfate, but we've also got some potassium sulfate. So what that means, again, if we draw this out, which I always recommend drawing out these types of problems just for clarity's sake, you're throwing in your chunk of calcium sulfate again. So we're asking the same problem: how many moles of the calcium sulfate are going to be soluble per liter of that liquid, or that solution, in this case water. But this time we have an existing ion concentration in the solution that's common to one of the ions that's going to actually dissociate, which means we've already got 0.1 molar sulfate ion hanging out in solution. We also have 0.1 molar potassium, or actually 0.2 molar potassium because there's two of them there. But really, for the common ion consideration, we're really only concerned about the sulfate. So same setup to begin with. We're going to make an ice table, and to do that for a solubility product problem, we need to write this out from the perspective of the dissolution of the solid, which turns into calcium 2 plus and sulfate ion. We'll write this out as initial change and equilibrium. We don't have any calcium sulfate to begin with. We do not have any calcium 2 ion to begin with, but we do have some amount of sulfate ion in the system when we start, which is going to be 0.1 molar. Again, we're going to have some amount X of the calcium sulfate that dissolves, 1 to 1 here, so this turns into an addition of X of calcium ion that grows into the solution or dissolves into the solution. And now for sulfate, we're going to have whatever the original concentration is plus some amount X, again, the X coming from the fact that the balancing coefficients here are just 1 to 1. So at equilibrium, we're going to have essentially 0 minus X of this stuff dissolved. So X amount of it will dissolve into the system. Again, that's not important because it doesn't factor into our equilibrium expression because it's a pure substance. We'll have X calcium ion, and we'll have 0.1 plus X as our sulfate concentration. The KSP is identical, right? The KSP for calcium sulfate doesn't change. It's a constant that's based on thermodynamics, based on delta G for this reaction system, this dissolution. Let me look that up really quick. What was that value? That was 2.4 times 10 to the minus 5. And so if we set this up as an equilibrium expression, again, it's going to look the same. KSP has to be equal to the product of the resultant concentrations of the ions, so calcium 2 plus times sulfate ion concentration. So what's happening here? We know common ion effect is telling us, from Le Chatelier's principle that, we're ramping up this thing. So if we're ramping up the concentration of this, but we know this to be true, that the concentration of sulfate times the concentration of calcium has to equal a constant, which is the same constant that we have if calcium sulfate's the only thing in solution, then we know this thing's going up, which means the calcium has got to be less than what it was before. How do we yield less calcium to solution? Well, that means we just have to dissolve less calcium sulfate into solution. Right, we just got a little bit more sulfate than what we started before. So how do we set up this expression? Well, we just plug these values into our original expression. So let me scroll this up a little bit, maybe zoom out so we've got a little bit more room. So this turns into plugging in X for this and 0.1 plus X for this value. So we end up with KSP equal to X times X plus 0.1, which is equal to X squared plus 0.1 X equal to 2.4 times 10 to the minus 5. This is the full expression, so X squared plus 0.1 X minus 2.4 times 10 to the minus 5 equal to 0. This is our beloved quadratic expression. So we have a couple different options in solving this. So our two options are either to solve this thing quadratically. So here's the quadratic equation. You probably have that committed to memory. So in this case, A is going to be whatever the coefficient is in front of the squared variable, which is X. B is going to be whatever the coefficient is in front of the X, the non-squared value, and then C is going to be this quantity here. We can input those values. We're going to get perhaps two X values for this because of the plus or minus function. But if you get a negative value, that's unrealistic. Sometimes you'll get two positive values, but only one will ever be realistic. And I'll talk about where and how that is. So if you solve this quadratically, you'll get the right answer every time, without a doubt. But we can also make assumptions. And I want to show you how to make assumptions because as is sort of relevant in this class, a lot of what I want you to come away with is less how to be really proficient using a quadratic equation, which most of you are going to punch this into a calculator, pop it into a quadratic equation computer program on a Chrome browser. That's not super helpful. What I want you to start to think about is intuitively, what does this mean, right? So if you have a KSP which tells you that the concentration of your two ions have to, when multiplied together, equal this value. How can you use that value to quickly ascertain um, whether or not X is going to be big or not, whether or not this thing is going to be soluble or not, right? And what this tells us, right, is that if the K is really the product's concentration over the reactant concentration, obviously weighted by their coefficients, if you have a value that's really small, 2.4 times 10 to the minus 5 is essentially the same as 1 over 10,000 ish. That's ballpark, right? That's the 10 to the minus 5 here. So 1 over 10,000 really tells you that you get one product for every 10,000 reactants. So this thing is really insoluble, right? Quite insoluble. So what does that mean regarding your intuition for the extent by which the calcium sulfate is going to dissolve? Well, it means that it's not going to dissolve very much because the ratio at equilibrium is 1 to 10,000, roughly. So that can mean that X here is going to be really small because it's not going to, well, it really means that this, whatever that value is times whatever this value is, has got to equal 2.4 times 10 to the minus 5. So if those values are really, really small, then especially relative to 0.1 here, then it's going to be fairly inconsequential to our overall concentration chain. So if we do make this assumption that X is considerably smaller than 0.1, what that really means is by adding X, the sulfate concentration really is nominally the same as 0.1. That's our assumption. And if that's true, then it doesn't make sense to go through and solve this quadratically. If the only thing that changes in that computation are several digits past what our significant digits are or past the error of the measurement, then there's no purpose in calculating them because they're insignificant to the overall value. So if we imagine this is our expression, right? X times X plus 0.1 is equal to KSP, which is 2.4 times 10 to the minus 5. If X is really small, and if it's considerably smaller than 0.1, then it's this part of the algebraic expression that would change as a function of this assumption. That's where the assumption manifests. Because if X is tiny relative to 0.1, then this X is nominally 0, right? Because adding it to 0.1 doesn't change anything. It's so small, it's essentially 0. So this expression gets truncated and it turns into 0.1x because this X gets distributed here. And that is equal roughly to 2.4 times 10 to the minus 5. So we can just compute this, and this turns into X equal to 2.4 times 10 to the minus 4 molar. So that's a pretty small number, right? So if we have 0.1 as our original sulfate concentration plus 2.4 times 10 to the minus 4, which is the same as moving this out 1, 2, 3, 4, which would be the same as 0.12324 plus 0.1. That's essentially what we're doing here. It becomes 0.10024. Is this consequential? Well, it really depends on how many significant digits you want to retain or can retain in your computation. Because the original concentration was 0.1, and if you're only keeping 3 sig figs here, then this addition of the 0.24 is a negligible change and it doesn't matter. In some cases it does matter, and that's really where you want to start thinking intuitively as a scientist. So if you remember back from Chem 108, to check our assumption, sometimes we'll make this assumption. It's just more convenient than doing quadratic, but again, use the quadratic every time, you'll get the right answer. So to check the assumption, we'll take and just look at the ratio of the change, which would be 2.4 times 10 to the minus 4 divided by the original concentration, just to see what fraction of that concentration changed, times 100. And in this case, this equates to 0.24% change from the original value, which was the original sulfate concentration, 0.1. So it only changed by less than 0.25%. In Chem 108, we often said that it was okay, so we'll say this is 108, it was okay if less than or equal to 5%, which gave us a 5% error window. We said, if it changes that much, no big deal. I'm not going to put down a value for you per se, but I'll say generally okay if less than or equal to 1% unless otherwise noted. There are circumstances, and I always bring up medicine, where that quarter of a percent change is the signal. That's it. That change is what you're trying to measure. And that can be the difference between the life and death of a patient. In other cases, it's not important, and you wouldn't have seen it because you weren't keeping more than 3 significant digits anyway. So it's important to start to think about error, significance, and change, especially in equilibrium concentrations, so that you can get a bearing on what's important and what's not, and make those decisions for yourself, like this sort of criteria here. Often you're not going to have somebody that says, yeah, 1%'s okay, or 5%'s okay. You're going to be the scientist, and you're going to have to determine, is it okay within the error that I'm computing and with the end use of the data that I want to use it for. So if we go back to our original set of examples we were going to look at here, our new computed value when we had existing amounts of sulfate dissolved in the solution was 2.4 times 10 to the minus 4 molar. So if we look at that, that's just about a 1 order of magnitude decrease in the solubility of the sulfate ion, and that simply just came from the presence of the sulfate coming from the common ion effect. So that's a direct sort of pronouncement of that phenomenon. So what happens then when you have salty, briny solution, but you're not considering any common ions in the case of KNO3? Well, that's going to take a little bit of revisiting. So the convenience of recording videos is that normally I'd thread in part of Chapter 8 here, but what I can do is say just watch the first part of Chapter 8 on activity and then come back to this, and then the punchline will be a little bit more obvious and resounding. So I'm going to walk through this example, and I will say pause this and watch the first part of Chapter 8's video. So we already walked through 2 examples here where we had just calcium sulfate dissolving in water and then calcium sulfate with some common ion in water. Now we have calcium sulfate with just what we'd consider spectator ions. Potassium nitrate, super soluble, so all those are going to be in the beaker already. Well, how that's going to impact my overall solubility of the solid. In order to understand this, we have to understand that the concentration of ions is governed more explicitly by this notion called activity. So concentration and activity are related to each other, but they're not the same. So activity explicitly includes the effects of other ions in solution that are not the ion specifically participating in equilibrium. So other things present. Whereas concentration, as you know, when we think about the concentration of an ion, we don't consider anything but literally the number of moles of that thing per the liter of solution volume. That's what concentration is to us. Activity is an extension of concentration where it specifically includes whether or not you're talking about the concentration of something in pure water or the concentration in something like ocean water. So the activity of an ion requires us to really know, well, what ions are in solution and have a quantitative measure of that. So how many other ions are in solution? And we use this thing called ionic strength, which I think the name implies, the amount of ions dissolved in solution that are not the thing that we're relating to specifically for concentration. So the ionic strength of a solution is something that can be computed pretty easily. And as I mentioned, if this looks totally foreign to you, pop over and watch the first little bit of Chapter 8, and that will clarify things extremely. So ionic strength is going to be equal to 1/2 times the concentration of ion 1 times the charge of ion 1 squared plus the concentration of the second ion that's in solution times its charge squared, etc., etc. So we can generalize this as 1/2 and then summation over ith species, Ci, and then the charge of I squared. So you you're computing the ionic strength, and this is going to be in units of molarity, is you are taking its concentration in moles per liter times its strength, or I'm sorry, um, its charge squared, and then you're adding all those up. So this would be ion 1, this would be ion 2, ion 3, etc., depending on how many ions you've got in solution that are fully dissolved. That's going to give us this quantity ionic strength, which is a proxy for what do we have in solution and how many. And then we're going to use that to factor back towards computing this thing called activity, which is really concentration corrected for whatever else is in solution. And so in terms of equilibria, we know that the equilibrium constant in its traditional sense of how you're used to thinking about it is going to be equal to the product of the two ions that dissociate. But when we're talking about activity, so this is from concentration perspective, which is what we've learned all the way up to this point. But in reality, because we're never talking about ions that are dissolved in pure water absent of everything. There's always going to be even a trace amount of something. Even in deionized water, nanopure water, there's always going to be a little bit of other stuff, and those things are going to influence the hydration sphere that surrounds these, how water actually coordinates around these ions. So in reality, the equilibrium constant is equal to the activities of calcium times the activities of sulfate raised to whatever that power would be. In this case, it's 1 because the coefficient is 1 in the balanced chemical reaction. And when we talk about activities, as the first part of chapter 8 will refer you to, activity really is the concentration, the original concentration, so calcium 2 plus, times this thing called the activity coefficient, which goes as a gamma. Here, each of these raised to whatever power we need them to be raised to. So KSP is equal to, in this case, the concentration of calcium multiplied by this adjustment factor, which is the gamma calcium, which is the activity coefficient. That's all multiplied by then the concentration of sulfate in solution multiplied by its correction factor, sulfate. And so I'll show you how to compute those correction factors. Those values are anywhere from 0 to 1. And they'll augment the actual apparent concentration of calcium in solution. And so this is the true way, using activities to relate to our overall equilibrium constant. So these activity coefficients here, this is the new thing that you haven't seen except if you've watched chapter 8. These two things are related to the ionic strength, as I mentioned before, and I just a minute ago showed you how to compute that. So in this example, we're talking about 0.1 molar KNO3, so we want to consider the ionic strength of the system. That will allow us to compute these gamma values and adjust our equilibrium expression for the activities instead of simply concentration. So we first have to compute the ionic strength of a 0.1 molar KNO3 solution. So again, using that expression, that's going to be 1/2 times, let's see, and that will be 1/2 times 0.1 molar potassium, because this is going to break apart into potassium ions and nitrate ions, each at 0.1 molar. So it'll be 0.1 molar times the charge squared on the first ion. So if we're doing potassium, this will be 1 squared. So this is for the potassium ion here. Plus, this is the summation part, the concentration of the nitrate ion, which would be 0.1 molar, times -1 squared, which this component comes from the nitrate part, and that's it. So this value, if we compute it, let me compute it really quick, is just going to equal 0.1. So that's 0.1 molar, and that comes from 0.1 plus 0.1, and then the half. Don't forget the half. So our ionic strength of this solution is 0.1 molar. So then that value, as chapter 8 video will show you, will feed in to compute the activity coefficients for both of these. It will adjust the apparent concentrations, and from that we'll be able to compute our actual equilibrium concentration. So computed, those two activity coefficients are, for calcium, are 0.405, and for sulfate they're 0.355. So those values would get factored into our sort of adjusted equilibrium expression. So now KSP here is equal to our calcium concentration times 0.405 times the sulfate concentration times 0.355. So since we're considering still the dissolution, we can write up an ice table for this just as we would have with calcium sulfate by itself, like in part 1. And it's the same thing. We get some amount x of both of these that are going to dissociate, and so we can actually just substitute x in for calcium and sulfate because they're going to be the same. That's the sort of takeaway there. Both the concentration of calcium and sulfate will be 1-to-1, will be the same, so we can substitute x in for each of these. So the KSP here is going to be equal to x times 0.405 times x times 0.355. So we can divide into the KSP first the 0.405 and the 0.335 or 355 values, and then we'll have that equal to x squared. So the 2.5 or 2.4 times 10 to the minus 5, this is the KSP. 0.144 is just the 0.405 multiplied by the 355, and then collecting like terms gives us x squared. So we can solve this, and this gives us a value x is equal to 0.013 molar. Okay. So again, I'm going to remind you, if you watch this, that's totally fine, but certainly watch the first part of Chapter 8 video just to ensure that you understand the origins of these, because I'm not describing exactly how I got to my activity coefficients, though it's pretty straightforward. So you can cycle back to this and maybe have a more reinforced punchline here. So essentially what we did is exactly what we did with just calcium sulfate. The exact same ice table. The only thing that differed, if you look at it, is this. That's it. This expression, when we did it with just calcium sulfate, we didn't include these two adjusting values, which we're adjusting for the activities of the solution based on the fact that there's some amount of potassium nitrate to begin with. In this case, we have these factors, which essentially decrease the apparent concentration of calcium and sulfate, right? Because we're taking calcium, the original concentration, and we're essentially multiplying it by 40%. We're taking the sulfate concentration, and we're essentially multiplying it by 35.5%. So the apparent concentrations of each of these are much lower in solution. If that's true, if those are much lower in the solution, that means more of the calcium can dissolve, right? Or more of the calcium sulfate can dissolve, because those concentrations are essentially being suppressed by the fact that there's some KNO3 that's in solution already. And we'll talk about that in Chapter 8 and the shielding effect and what causes this exactly. But the sort of punchline here is that the molar solubility of calcium sulfate here, X, is 0.013 molar. So if you remember, and we can zoom back out and go back to our original scenario, if you remember what that meant relative to our other scenarios, that's considerably different, right? We can put 0.013 molar. So now we're talking about three different situations. One where we have calcium sulfate by itself, which has roughly 4.9 millimolar solubility. We have with common ion, which is essentially 0.24 millimolar. And then we have with this other salt that is not a common ion, in which case we have essentially 13 millimolar. So we've got almost a factor of 3 increase in the solubility when we've got another salt that's present in solution that's not a common ion. So we get the exact opposite effect of the common ion, and this comes from this notion of ionic strength and shielding, and actually lowering the effective or apparent concentration of those ions simply by surrounding the calcium and the sulfate ions with the potassium and the nitrate ions.